Okay, so the last chapter and the last 2 weeks of this semester. Okay. You can see I'm starting with a clean board here because there's nothing to write, but I hope all of you still remember what we have been doing so far, at least the basics of it. I don't expect you to remember each and every detail. Okay. This is the time when we kind of merge everything and apply both derivatives and integrals to vector fields. Okay. So chapter 4. So at this point, the content of this course is mostly physics and engineering. Okay, there is not a lot of applications of this outside of what you would see in maybe fluid mechanics or electricity and magnetism. Okay, those things are what governs this thing here. So very traditional and very important part of math, which led to a lot of revolutionary discoveries later. Okay, so I'll talk about a few of those as we go along, and so a little bit difficult to get an intuitive understanding of everything that happens here, especially in a summer course. So don't feel bad about it. Okay, the key thing is to just not fall behind and be able to do the problems. Okay, and then understanding some of these things will take some time. That's not your fault. Okay? Because it took a lot of smart people a lot of time to develop these things. So you have to kind of appreciate that and be humble about what you're learning. All right, so the only two assessments remaining at this point. There is a quiz on Thursday, which will cover what we do today and maybe half of what we do tomorrow. Okay, so quiz 4 on June 17th. I dropped one quiz, so if you feel like skipping a quiz, this is the time. Okay, but I don't skip in it. I don't drop any tests. So test number 3. I'm planning to do this on 6/24. Okay. Now, if any of you have any strong objections to it, just email me and let me know. I can move it to June 28th. I know some of you probably won't want to have a test in a certain period before the final exam week or something. Okay, if that's the case, just email and let me know. I'll move the entire thing to June 28th. Okay, so yeah.
Is there a final exam?
No, there's only 3 tests: test 1, test 2, test 3. So if this is moved, it's going to be just test 3 moved to the final exam week. Yeah. So I don't have a cumulative final exam. I know all of you are dying to write one, but I don't have one. Okay. So that's something. If you have any strong objections, let me know by the end of this week. Otherwise, we'll assume that it's on 6/24. Okay. And I hope we should be done with all the material by next Tuesday, as usual. Okay. All right, so any questions before we start? I know there's nothing at this point. Okay, so far in chapter 2, you did partial derivatives. You should know how to still find partial derivatives. And the one concept I want you to remember from that particular chapter is the definition and the meaning of the gradient vector. Okay, you shouldn't forget what that looks like. And chapter 3, we did multivariable integration. All those things we learned in chapter 3 will be useful here because, of course, it's integration on vector fields. Okay, so polar coordinates, cylindrical coordinates, spherical coordinates, everything we learned there, and also the surface area. So all those concepts are going to be kind of taken for granted here. I'll drop one quiz no matter what. Okay, I don't judge people on why you're going to miss a quiz. So if you just want to take quiz 4 off for whatever reason, that's okay with me. Okay, no questions asked. So one quiz dropped unconditionally. Whether you fall asleep or just don't want to write it. Okay. It's one less quiz for me to grade. So, all right. So section 4.1. It's always good to write it as a practice. Introduction to vector fields. So in this title here, the word field means just a collection of things. Okay. So if you look at the weather map, for example, if there's a really windy day, and if you have a certain region, you will probably see this things which denote the wind velocity on a certain day, 40 miles per hour, 50 miles per hour. Okay, that is in a way a vector field of the wind speed or the wind velocity. It's easy to kind of, for a layman, it's easy to look at that and say, oh, it looks windy or it doesn't look windy. Okay. So that is the idea of a vector field. So let's give a mathematical meaning to that. So let f of x1, x2, dot xn be a function in Rn, which means there are n variables. Okay, so we'll be mostly living in R2 or R3, but it could be any number of variables just for fun's sake. Then a vector field, capital F, it's a vector of x1, x2, x3 dot xn is a vector and a function. Okay, so let me just write it more precisely here. So it's a function that outputs a vector for each point. So each and every point that you're trying to represent is associated with a vector. Okay, that is what a vector field means. So if you have taken physics courses, you have seen plenty of examples of this. Okay. Examples: gravitational force, you can think about Earth and the Moon sitting, okay, in space, and then you have forces acting from all sides because of each of these. Okay. This is Earth, this is Moon. So that's a gravitational force field, or it's just gravitational force. It's a vector field. Okay. So every point in there will have some kind of a force vector, which is either pointing to, pointing away, depending on where you are. Electrical field, you have some kind of charged particle sitting there. There is a field generated by it. Okay. You cannot see any of these things. These are all abstract things that we say we feel it, right? You cannot really see electrons flying around in space. So you have to believe that there is an electrical field, which is what creating all these things. Okay. Magnetic field. The most familiar one to you at this point, based on your calculations this semester, must be the gradient vector field. Because we have done direct calculations for this. If you're given a function of xy or xyz, you know how to find the corresponding gradient vector and plot it if you want. Okay. That will give you a set of vectors in R2 or R3. So for example, if you have f of xy equal to x squared plus y squared, okay, you know the gradient of f. Okay. Maybe you forgot it, but it's the vector whose components are the partial derivatives, and that's equal to 2x, 2y. It's a vector. It's not 2x plus 2y. Okay, 2x is the x component, 2y is the y component. And if you want, you can even plot it on the xy plane. You can sketch reasonably easy vector fields by hand. It's not a big deal. Okay. So sketch this vector field. What do? You draw a table, okay, just like you do it in your middle school when you want to plot something. You just draw a table, give some values. So this is x, y, and this is now your vector field, capital F of x, y. Okay, so you got a function, that's a scalar function, and you got this vector out of it, okay, f of x, y. And because of the way we denote a point and a vector by the same notation in the textbook, this is now a vector, so these are components, okay, not coordinates. Let's give some sample values here, x equal to 0, y equal to 0. That's just the 0 vector. It's 0, 0. That's 0, that's 0. So that's just a point. It's not going anywhere. It's just stationary there. Let's give x equal to 1, y equal to 0. When x equal to 1, y equal to 0, you get the vector 2, 0. Which means you've got an x component of 2 and a y component of 0. Which means it's on the x-axis. 0, 1. These are my typical sample points because being on the axis and some convenient points will give me some idea about what's going on. 0, 1 is going to give you 0, 2. Since I'm running out of room, let me create another table here, x, y, and f of x, y. So we're just doing it the old-fashioned way, okay? Assuming that you don't have a computer or a calculator, that's what you would have done. X equal to negative 1, y equal to 0 will give you negative 2, 0. Okay, and these are vectors with components, not points. Okay. 0, negative 1 will give you 0, negative 2 as a vector. And if you're thinking that I'm just being a little too convenient by picking zeros and ones, okay, you can pick a general point if you want, say 1, 1, just to see what happens if you go in an arbitrary direction. Okay. That's going to be 2, 2 here. Okay, you can generate more points if you want, but if you plot these vectors, okay, it should give you some idea about what to expect in general for that entire vector field. All right, so let's draw a beautiful XY plane and then start plotting all those vectors. Only plot 2D vectors by hand. 3D vectors would need a software or some kind of an app. Okay. So 0, 0, well, that is just a point here. 2, 0, well, it's 2 units to the right and you're not going up anywhere. Okay. So it's going to be this vector here, 2, 0. So on the x-axis, 2 units to the right. 0, 2, well, these are not any fancy things that you're drawing here. Okay, this is 0, 2. Negative 2, 0. So just keep in mind that if it is a positive x component, it's to the right, negative x component to the left, positive y component up, negative y component goes down. So negative 2. So if this was representing a fluid flow, okay, you can think about it as some kind of a fountain sitting at 0, 0 and just ejecting fluid out on all the sides. Okay. It's flowing out that way, up, down, left, and right. Okay. It's not going into it, it's going away from it. Okay. But you might think, oh, I just chose some convenient points. Let's look at 1, 1. Okay. When you pick x equal to 1, y equal to 1, the vector is 2, 2. So that's sitting somewhere here. Both are positive, but it's not really along any particular axis. Okay, So it's what, northeast. And similarly, if you were to plot negative 2, 2, it will go here. And negative 2 would go here. And 2, negative 2 will go here. So the good thing about getting these sample points is that now we know what happens everywhere else. If it started here, for example, it will just go out like this. Okay. Start here, it goes out like this. Start here, it goes out like this. And that's how you fill up a vector field. Take a sample set of vectors and just fill it up. Okay. Yeah.
Did you sort of determine the shape of the original function given the vector field? Like we know it's
That function there, no.
no.
No. And that's, I mean, you have some idea in your mind. You're kind of prejudiced about, it's a some kind of a paraboloid, but you won't get that paraboloid from here. That no. This is kind of on a 2D. We are only taking vectors that goes along. I mean, it is that surface, but not based on this. Yeah. So this is a vector field. Okay. F of xy equal to 2x 2y. I want you to observe one property here. If this was representing a fluid flow, it is just coming out of that one point in the center. Okay, from the point 0, 0, everything is flowing out. Okay, represents a divergent flow from the point 0, 0. It's almost as though we have some kind of a fountain there, and it's just sending these fluid particles along all possible directions. Okay. So such a point is called a point source. For obvious reasons, things are coming out of it. What do you think the vector field for this one would look like? Let's get rid of the 2. The 2 is not doing anything useful. So negative x, negative y. What do you think would be the vector field? I'm just negating those two things. Instead of x, y, negative x, negative y, okay, without bothering about the 2. What kind of arrows do you expect now? Going into that, right? So instead of going out, all the arrows will point into it. You can sit down and draw a table and all that, but it's going to just be opposite to whatever you were seeing earlier. Okay. So everything kind of culminates into that point 0, 0. What would be an appropriate name for this point now? Everything is going into it. You have seen this happen in your kitchen, for example. We call it a kitchen sink. So that's called a sink. Okay. This name should be intuitive, right? If it is named as some kind of quantum mechanics thing, you wouldn't know what it is. Sink, you know what it is. Things are going into it. Now, can you draw the next one and tell me what exactly you observe? So example 3, if you want to call this a 2. Okay. Sketch the vector field of xy equal to negative y x. It's not negative y negative x, it's negative y x. So draw a table and see what kind of a pattern you get out of it. Negative yx. This thread usually covers some critical parts of the chalkboard. By the way, this is called a convergent flow or a negatively divergent flow. Okay. Usually people call it as negatively convergent, so negatively divergent flow, okay, because it's going in. Where?
Where do you put the tail of each individual vector? Because if you were to draw negative, like the vector field of negative x, negative y, with every tail originating at the origin, you get the same exact vector field as 2x, 2y.
The tail, it should be at that particular point. It's the point is the input, the vector is the output. So if you input the point 1, 1, for example, the tail should originate at 1, 1. Though, we're not going to scale, so it might be a little off. Got a question? Okay. All right, so that's, you don't have to get stressed out about it. Just do it in a fun way. Yeah, I won't ask you to sketch it on the test or anything. Again, 0, 0, nothing happens. So remember, it's negative yx. Okay, so you're not only flipping it, you're also negating the y coordinate. 0, nothing done. Okay, 1, 0, 0, 1. Negative yx. Flip and negate. Just for sanity reasons, let's also take a point 1, 1. X, Y. Okay, so the point 1, 0 is here. Okay, and from there the vector is 0, 1, which means it's pointing in the positive y direction. Okay, so from the point 1, 0, the vector 0, 1. Okay. 0, 1 means it has got no x component and 1 unit along the y axis from that point. Okay. So there is this one. At the point 0, 1, where do you think it's going? Left, right, up, or down? This left, okay, because x is negative 1, y is 0, so it's going to the left. At negative 1, 0, again, none of these are drawn to scale, so it might look a little awkward. But at the point negative 1, 0, where is it going? Up, down, left, or right? Down. Okay, it's 0, negative 1. So a negative y component means it's going down. It's nothing like the previous one, right? The previous one looked like it's going into or away from the origin. This one looks something else. Okay. What about this one? Sorry, this one here. 0, -1. Is it going up, down, left, or right? To the right. Well, just to make sure that our intuitions are correct, let's also pick a point 1, 1. Okay, so it's somewhere here. It's going, when you say -1, 1, that's left and up. Okay. So vector that will be left and up would look like this. So if you're here, it will be left and down, okay, right and down, right and up. What is the general pattern you see here now? If this were to fill in with millions of vectors, what kind of a shape will this create? Spiral kind of thing. It's not, oh yeah. When the vectors will just go around this one. Right? When it's a spiral, it kind of looks like it's going into it, but these are just going around it. Okay. But the orientation is important here. It's going in the counterclockwise orientation. Okay. So it's what you call as a rotational vector field. So if you were to do y and -x, it will be a clockwise rotation. Okay. So it's a rotational vector field with counterclockwise orientation. These are the two characteristic kinds of motion, whether you're dealing with fluid particles or with electrical charges or magnetic flux lines, whatever it is. Okay, the two characteristic kinds of motion that you're going to observe are divergent and rotational vector fields. That is what is illustrated here, whether it's in R2 or R3. Okay, R3 I cannot draw it because it's too complicated, but these are the two important concepts that we'll be dealing with this semester. Okay, either it's going out or in, or it's going around, or a combination of both. Okay. Right now, I didn't draw anything with a combination, but it will also be a combination of both divergent and rotational fields. Yeah.
Out of curiosity, are each of the vectors in that rotational vector field perpendicular to the given point?
Given point,
Like if we were to draw,
it will be perpendicular to the level curves if you draw it. If you take the function, draw the level curves, then these vectors are going to be kind of perpendicular to, because it's gradient vectors. So that question by itself needs more information to complete the answer, whether it's perpendicular. And if you look at just weather maps and all that, they use different lengths for this vectors so that the people looking at it has some idea about how strong or how weak those vectors are. Okay, so usually if you're drawing it properly, the length of the vector should represent how big or how small things are. So I'll show you a couple of examples on GeoGebra just to show you how it is done more professionally, and that way I can share the screen with my people who are on Zoom. And here. Yeah. So this is the same vector field, which, if you just search on GeoGebra for vector fields, you don't have to draw this by hand. Okay, you can always draw any complicated vector field using this. You can see the vectors are of different lengths as you go away from the origin, and that's because it's getting scaled with appropriate values of x and y as you go outwards. Okay. But the common feature here is that it's still a set of vectors that goes around in a counterclockwise orientation. So now you don't have to do this by hand. You could just go here and start playing with it. Okay. So if you have, say, y and -x, it's the clockwise orientation. So the arrows go the other way instead of going counterclockwise. And if both are negative, it's what we call as a saddle flow because it doesn't go around or towards, it kind of looks like it's going in, but it's going out. Okay, so if you follow these arrows here, okay, it kind of goes in and it kind of goes out there. So it's a very deceiving part if both are negative or both are positive with the x and the y interchanged. Okay, so that's what I call as a saddle flow because it's neither here nor there. And similarly, the vectors from here will kind of go up here and exit that way instead of going into the origin. So these are all things that you can explore by just taking GeoGebra, just input the vector field components. You don't have to draw it by hand, okay? Just to get an understanding of what it looks like. But don't forget these two, divergent and rotational vector fields. Okay, that's what we're going to spend a lot of time on. And let me also show you how to, or what you would see in 3D. So let's start with something with X, Y, and Z here. I cannot draw this by hand. Okay, so this is a vector field in R3, and you can see that all the arrows are kind of starting from the origin and pointing outwards as though the source is sitting at the center. Okay, and those jet of fluid particles just going in all directions. And forgot what the rotational one looked like. Let me see, Y, Z, and X maybe. Oops. Yeah. So if you kind of orient it in the right way, you can see some kind of tornado kind of thing, okay, going in circles. There is no divergence here, everything is going around. Okay. So that is a vector field in R3 with very straightforward components, Y, Z, and X. Okay. All right, so that is how vector fields are drawn and understood. Okay, if you take a crazy vector field and try to understand what is going on, it might not make a lot of sense. So, for example, if you go Y plus sine of Z, then it kind of gets messed up all over. So it's probably not going to make a lot of sense there, but at least you could use this to get all kinds of vector fields. All right, so that is the definition of vector fields. Okay, now I want you to, now that I'm sharing the screen anyway, let me also do this. I want you to watch this video carefully. Okay. I think I've started at the right point. Please pay attention to this because once we start the calculation part, we won't get time to come back to this one. Okay. I would strongly recommend that you kind of watch the videos by this 3 blue, 1 brown. Those are excellent math videos if you are taking math courses. Okay. So I hope the audio. Yeah. Let me just go back a little bit.
Around some points, but it seems to just spring into existence as if there's some kind of source there. Some other points act more like sinks, where the fluid disappear into nothing. Divergence of a vector field. Come watch this electric field. Tends to flow out of or for example, the divergence of a vector field evaluated at all points. Still insinuate a certain spontaneous generation. On the flip side, if it's small region around this the divergence in that. Remember, this vector field is a function that takes in two-dimensional and spits out two-dimensional numbers. Divergence of that vector.
output depends on the field. It's not it's analogous to a field. And that output is just a single number. How much that acts as a source or a sink. For this particular discussion of computations theory, for what it represents is one. This means that for an actual physical fluid, whether water, some imagined arbitrary vector fluid, and if that fluid is incompressible, the velocity vector fluid must have divergence of zero and everything. That's an important constraint of what transit solve real world fluid flow problem. For the curl at a given point, we also think about the fluid flow around it. You ask how much that fluid has to rotate around. Is it if you were to drop it, somehow fits in the same spin around. Region fluid application is clockwise, or so they have a positive curl, or it's counterclockwise. It doesn't have to be that all the vectors all of them inside a region like this one, but also have non-zero curl. Since the flow is slow at the bottom, the width up resulting in a net clockwise. Really, true proper curl is a two-dimensional one where you associate each space with a vector characterizing rotation. And I explained it properly to my pattern. For our main purpose, I'll just be referring to two-dimensional, which associates each point with a space with a single vector. As I said, even though these intuitions are given in the context of fluid flow, what we say is are significant for other sorts of vectors. What's very important is how electricity and magnetism are described by four special equations.
All right, so let's just stop there. Okay, let's not kill the fun now. Those are exciting things for later. Okay. All right. Oh, sorry about that. If the audio was, I didn't know that. Yeah, but it's. I don't know what I could have done here to. Isn't that something that listeners can control, or I don't know. All right. Anyway, yeah, I can send you the YouTube link again on on Canvas. So again, the whole idea is that even if you didn't hear all the commentary behind it, let me just write down the important parts of what he was trying to say there. Okay. So definition 1, divergence of a vector field. So this is the part where he was showing all those arrows either going in or coming out of a certain point, okay, or even a certain region if you are considering the fluid flow. So if this is how the fluid is flowing, okay, and if you take a certain part of it, and if you want to know how much fluid is either coming out or going in of this small part of that entire region, okay, that is what is measuring the divergence. So let F be a vector field. I'm going to define in a very generic way so that it won't, you don't have to bother about what units and everything you're using. Okay, so let F be a vector field. And this could be in any dimensions, say Rn. Okay, so it has n components. The divergence of F what divergence should either tell you everything kind of going in or coming out. Okay. That is the meaning of the word divergence. So there's nothing going around in a divergent flow as such. Okay. So the divergence of F measures how much. So I'm going to use the word fluid in a generic way. It could be electrical flux or magnetic flux or whatever. Okay, how much fluid either goes in comes out of a certain point in the vector field. That is the physical definition of it. Okay. That video did not show you how to calculate it. It just showed you that a positive divergence means it is coming out, a negative divergence means it's going in. Okay. That is just a sign convention. So this is a positive divergence, that's a negative divergence. Yeah.
So how does that apply to the points to the left? Is that
Points on the where?
that like point that you drew right there?
Uh-huh.
Like, how does-
So if you want to say how much volume of fluid is passing out of this particular circular region per unit time, okay, that is what is measured there, or how much is going in at a certain time.
Okay, so let's say like the vector field was just a constant, just a set of constant magnitude vectors pointing in one direction. Would it be zero then?
Yeah, it'll be zero.
Okay, so
Yeah.
it's the same amount that's coming in as it's going out.
It's zero, yes. Okay. That is where all the equations of fluid mechanics start with that assumption that divergence is zero because matter is neither created nor destroyed, right? It's a law of conservation of mass. Yep. So zero divergence means there is nothing going in and nothing coming out in as a net amount. Okay, something could be changing inside, but in general, nothing is changing overall. So the divergence of F denoted by div F is greater than zero if flow is out of the point that's the sign convention. We have to fix something as positive. The outward flow is divergent. That's a positive thing here. Negative if the flow is into the point. And the divergence of F is equal to zero if the flow is steady or there is nothing that is created or destroyed in a net amount. Okay. No net creation or destruction of fluid. So even if the flow was just going around a certain point, there is no divergence there. Okay. Now, how do we do this mathematically? So there are two parts of this, the physical part, which is what the video was doing. Okay. To do this mathematically, we need some calculus because at the end of the day, there's how much flow is happening per unit something. Okay. It's always a derivative concept. So the computation part. Two definitions here. One, the divergent operator. It's also called the del operator. For those of you who don't want to say the divergent operator. It's denoted by this upside down triangle. It's a vector whose components are the partial derivatives with respect to each variable. So partial with respect to x1, partial with respect to x2, partial with respect to x3, dot, 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 partial with respect to xn. Okay. So right now it looks incomplete because it's an operator. Anytime you use the word operator in math, that means it's waiting for something to act on it. Okay. So your derivative without any variable is an operator because it doesn't know what to do. So that's the del operator. Okay. So if f F1, F2, F3, Fn are the n components of the vector field F. Okay. Here's the vector field. Then the divergence of F is defined by the dot product of the del operator, okay, also called the divergent operator, with the vector field F. It's also called the gradient operator because it looks like a gradient vector. Okay. So you're taking the dot product of this vector with the vector whose components are F1, F2, F3, and so on. Okay. So all that happens when your dot product is you're multiplying the components together. So that will be partial of F1 with respect to X1. Remember, it's a scalar, it's a dot product. Okay. F2 with respect to X2. F3 with respect to X3. Dot, dot, dot. Plus Fn with respect to Xn. So I know it looks fancy when you write the operator and everything, but at the end of the day, you're just adding the derivatives of each component along that particular direction. Okay. That gives you how much of flow is happening as a net amount as a result of this vector field at a certain point. So let's look at the examples we did so far. F of xy equal to xy. That is the first example we did, right? In this case, the operator is partial x and partial y. The divergence of this would be the dot product of the operator with the vector field. That is going to be the partial derivative of x plus partial derivative of y. What is that equal to? I don't think that's a complicated thing to answer. 2. Remember how this picture looked like when you drew the vector field? It was originating from this and going all 4 directions. Okay. So a positive divergence means it's just going out of that point. Yep.
So would the operator just be a second partial derivative if you get that with x?
Well, say it again.
Would the operator be the second partial derivative of like an original function?
Oh, you're talking about the function that created this one? Yes. Yeah. The vector field itself came from something. If that is a gradient vector, yes. Yeah. So I think your question was kind of biased towards gradient vectors, then yes. Yeah. Not in general. What is the divergence due to this one? F of xy equal to negative yx. All you have to do is take the partial derivatives and add them together. Okay. Nothing fancy here. It's 0. Does it make sense with the picture we drew earlier? So the partial derivative of y with respect to x is 0, plus x with respect to y is 0. Okay. This was a rotational flow, remember? It went around. There was nothing going into or coming out of it. Okay. So this makes sense because it was the rotational flow. Yep.
So do we define the divergence of F for the entire vector field or for like at a specific point?
You could do both. So you could do for the entire vector field, or you could just go for each point or each part of that region and do it as you like.
How do you do it for a specific point?
Oh, this is because because of these terms are already set up that way. If the terms were more complicated, then you'll have x and y terms to plug in. Yep.
So you choose like an X and Y point to plug into the vector field, get a specific vector, and then get the dot product of that with the
Operator.
operator.
Yeah. All right. So we'll do some examples in the worksheet. So just hold on to the divergence thought. Okay. Remember the second one about the curl. Okay. The curl of a vector field. As the word says, you've heard about curling iron and all that stuff. So it originates from the idea of a magnetic field curling around an electrical coil, or electric field kind of coiling around a magnetic field. Okay. So the curl of a vector field. This is a more complicated topic. Okay, be careful about how you're writing this. So it's only for R3 for the time being. So let F equal to PQR be a vector field in R3. The curl of F, which measures how much the flow rotates in a certain vector field. Okay. Which measures rotation. So divergence measures how much fluid is flowing in or out. Okay. Curl measures how much is being turned around. Okay, that's a more complicated concept. Okay. So which measures the rotation of the fluid in the vector field. Is given by the cross product of those two quantities that we wrote earlier. Because when a fluid rotates, it's not going straight, it's kind of trying to turn things around. Okay. So you need the cross components of each with whatever is on the other side. So it's given by the cross product of the del operator with the vector field F. So everything you've learned this semester is now coming back. Those are the things you learned in the first week of classes. Okay. So when you write this, be careful. Remember the cross product of vectors is written as a determinant with 3 rows and 3 columns. The first row is the ijk vector. The second one is going to be the terms of this operator. Okay. So it's going to be partial x, partial y, partial z. And the third one would be the components of the vector field F, which are denoted by PQR. Okay. So let's expand and see what each of these terms look like. As you would expect, the I component, this is a vector, it's a cross product. The I component would be the partial of R with respect to Y minus the partial of Q with respect to Z. Okay. I'm just going to use a subscript notation here. So it is partial R with respect to Y. R with Y minus Q with Z. So the X component just got the other two, Y and Z. Okay. Minus J times R with X minus P with Z. Don't memorize it, okay? Just do it for each problem, but I'm just trying to show you what to expect in it. The X component has Y and Z, Y component has X and Z, and the Z component has X and Y, QX minus PY. So that's a vector which is perpendicular to the plane of the vector field. Okay. Whose direction is given by the right-handed thumb rule. And precisely the reason why electricity and magnetism courses always insist on taking your right hand around and seeing what is the orientation of the resulting electric and magnetic field. Okay, so it always points in the direction of the right thumb. Yep.
Out of curiosity, the first vector that we looked at, is 2x and 2y. Will the curl of that be 0?
Yes, because it is a divergent flow, right? So a purely divergent flow has no curl, a purely curl flow has no divergence. All right, so let me just show you an example and then we'll do the worksheet. Okay. So let f equal to y, x, and z square. Find the divergence of f and the curl of f. Once again, you should know what these things are. That's a divergence, dot product is a number, curl, cross product is a vector. Sorry for kind of mixing up my writing there. Okay. Yeah, x, y, z. And if it makes it any easier for you, if you have 3 components P, Q, R in R3, you could kind of get that as a standard formula for the divergence as Px plus Qy plus Rz. So that you don't have to go through the entire operator dot product process. You're just taking the partial derivatives of each component with respect to each variable. Px plus Qy plus Rz. So what is that equal to? Maybe I shouldn't ask you, but that vector field up there. Anybody online? You want to tell me what the divergence of this one would be?
2z.
All right. So is it 0, 0, 2z or just 2z?
Just 2z.
Okay, good. Thank you. Those are the things you want to clear up today itself before you get too deep into this thing. The cross product, well, I don't know. You have to write it out. Okay. Now, I've seen students writing out this thing here and plugging it in. I don't mind. Okay. That kind of doesn't give you the full pleasure of going through this process. It's up to you. Ijk, partial x, partial y, partial z, y, x, and z square. It's going to be I times partial derivative z square with y is 0 and partial derivative x with z is 0. You have to still keep it there because it's a vector, don't throw it away. Okay, so plus minus j times you have z square with x and y with z. What is that? Z square with x and minus y with z. Zeros? Our hope is in the last one. Okay. What does that give you? That also gives you 0 because it's 1 minus 1. Okay. So it's a purely divergent flow, okay, with no rotation. This is just 0, 0, 0, and in fluid mechanics, it's called an irrotational flow. Means that the curl is equal to 0.
So when applying the divergent operator, do we treat whatever component of the vector field we're looking at as a function of like the variable that we're
Yeah. So in general, these are functions of, so if it's in R3, that's P of x, y, z, Q of x, y, z, and R of x, y, z. Is this what you're asking? Yeah.
So like when we took the dot product,
Mhm.
we were doing the partial derivative of y with respect to x, since there's no x in that function. It's just zero.
That's a 0. Yeah, that's just bad luck. 0. So that's not your fault, right? But in general, there could be any functions of x, y, and z. So let me write down a couple of applications of this, and then we will do those problems in the worksheet, just to kind of get used to the process here. Yeah, the divergence here depends on z. So at each point of z, we'll have a different amount coming out. That's because of the z squared term in the vector field. Once again, the applications are all kind of technical, so you have to pardon me if it is a little bit beyond what you might be expecting here. Okay. If you have taken physics 2, I think you might have seen this. So if E is the electrical field, then Gauss's law says that the divergence of the electric field is proportional to whatever charge density there is in the whatever thing you're looking at. Okay, so this Q is a charge density over some constant epsilon naught. In other words, if you have a negatively charged particle, you have got charges coming out of there. No, positively charged particle, you have charges coming out of there, and a negatively charged particle, you have going into it. That is the basics of electrostatics. Tells you that the total divergence of the electric field is proportional to the charge density available in the source or the sink. Okay. For a magnetic field, the equation becomes a lot more simpler. Now, does anybody of you know what this means? The divergence of a magnetic field is equal to 0. What does that mean?
supposed to just curl around something.
All right. So a magnet typically has 2 poles. Okay. So the magnetic lines always go like this. Okay. It doesn't go out into something like this or this. Yeah. Can you ever have this one? A magnet? Just one pole. Is that possible? So far, nobody has found it. Okay. So what this says is that there is nothing called a magnetic monopole. Okay. Physicists are very clever about how they write things, yet. Okay, so it's like a unicorn thing. Maybe it's out there. We don't know. Okay, so maybe one day we will find it, and that will change a lot of things. So right now, nobody has found a magnetic monopole. Okay,
Just break that one on the left.
like this one. I know people have asked that. That this becomes a south, that becomes a north. Can keep on doing this. Yeah, should I just keep on doing it? We cannot create a magnetic north, just a north pole or a south pole by itself. Okay, there is nothing called a magnetic monopole. The applications of curl, I'll talk about it later again. Okay, will show up in 2 different theorems in electricity and magnetism. One is called the Faraday's law. It's also called the Faraday's and Lenz's law. Okay, and also in Ampere's law. We'll talk about these two later. It's all got to do with how electricity and magnetism interacts with each other. So if you put a coil here and put a magnet inside it, the coil will generate some current. Okay, that is Faraday. And similarly, if you have a coil with some magnetic field through it, then there is a current generated here. Okay, that is Ampere. But there are more appropriate places to talk about it. We'll talk about it then. Okay, so I don't expect you to know any of these applications in a very strong way, but I need to understand the calculation parts of divergence and curl. That is the important thing from chapter 4.1. Any questions about this part? Let's look at the worksheet. Yeah, pretty easy problems there. Worksheet number, kind of lost track of numbers, number 12. So why don't you do problem 1, parts A, B, C. It's asking for the divergence and the curl of those vector fields. And you'll get a chance to do one similar things on quiz number 4. Okay. So worksheet number 12. You don't have to sketch anything, just do the calculations. Can somebody online tell me what the divergence of 1A would be? I'm expecting a number. Okay. 3. Yep. Good. As long as you're not giving me 1, 1, 1 as a vector, that is a good sign. Good. Curl of it. What's the curl for the first one? All right. So I've got 3 answers of 0, 0, 0, and there is one online. Any disagreements? 0, 0, 0. All of you are agreement with that, and it's not the number 0. Okay, it's a vector 0, 0, 0. Because none of these partial derivatives give anything useful. Okay. All right. Then please let me know if you want me to write more steps or want me to slow down. Okay, cruising on to number 2. Sorry for the distraction. Do you think these people did something useful and important in their lives, or are these things useful? We just take them for granted now, right? With all this technology and everything, it all started with these famous people, okay? Gauss, Faraday, and Ampere, and of course, in Maxwell. Yeah. Because we just take our iPhone and call people, but then a lot of history is sleeping on there. So 1B. ZXY. What is the divergence of F in this one? Did I copy it wrong? Okay. All right, let me see. I see one answer of 0. Any other answers of 0 for that one? What is your opinion? 0? 0, what about you? Did I catch you on a spot there? 0? Partial derivative of z with x with y with z, they're all equal to 0. Now that doesn't mean that it's a purely rotational flow unless you find the curl. Okay, so there is no divergence to start with. So if there is anything, it's going to be rotational. Okay. So the curl of F okay, so that's going to be I times the partial of y with y is 1 minus j times the other one is 0. Okay, minus j times y with x is 0, z with z is 1, but that's going to be a minus 1 because it's 0 minus 1, and then there is a negative from the determinant, and plus k times 1 minus 0. So this vector is 1, 1, 1, which means it's got the rotational component in all 3 directions. Okay, so it's almost like a hurricane that goes around the origin 0, 0, 0. So yes, it is a purely rotational flow. There is no divergence. The first one was irrotational and purely divergent flow. Any questions on these two? Just a silly exercise in partial derivatives, right? And 1C, there is no law that one of these have to be 0 all the time. Okay, the flow could be divergent and curling around. just like if you go and stand near Charles River, you would see the flow is going straight, and then at some places there will be some whirlpools and things like that, right? So x plus y plus z, and z plus x. Okay, so it's px plus qy plus rz. What is your answer? All right. Online, any answers? 3. Everybody seems to have a question mark with their answer. Also sound like a question mark. So 3. Oh, you're concerned that that is a 3, this is a 3. You can't have 2 3s in the same day. This no, just 3. I mean, it's just partial derivatives, right? It's 1 plus 1 plus 1, 3. But don't spend an hour on the test if you get the same answer on 2 questions. Okay. Just move on. All right, what about the curl? And I hope this is not equal to 0. That's why. All right, let's start. What is the x component of this? That's a 0 minus 1. Okay, so it's negative 1 minus j times, that's a 1 minus 0. That's a negative 1. That negative came because of this one. Okay. What's the k component? Negative 1. So again, these directions are decided by the right-handed thumb rule. Okay. Which is a lifesaver if you're taking E and M ever. Okay, the Lenz's law always points in the. That's what these rap musicians do all the time. So they use the right-handed thumb rule to do their dancing. All right, any questions about curl divergence? -1, -1, -1, yeah. Okay, now let's move on to the next topic. We'll come back to divergence and curl in various parts of this chapter. Please don't forget these 2 things. Okay, these are the 2 foundational ideas of chapter 4. Okay. So let's as a note before I start 4.2. If f equal to pq in R2, can we define some kind of a scalar curl for this vector field, just for calculation purposes? The curl of this vector field is a scalar actually the k component of the general curl that you computed earlier. Okay. It's given by the curl of f equal to partial qx minus partial py. So that's a number because we are now on the xy plane. There is nothing, there is no need for a vector pointing in the z direction. There is no z. Okay. So this is a scalar given by the difference in the partial derivatives of those 2 numbers. So if you look at your negative y x, the example that we did earlier, okay, this is p, that is q, the curl of f. This is called the 2D curl of f because it's only 2 components. There's qx minus py. Qx is 1 minus py is -1. That's 2. Which makes sense because our vector field look like this. Remember that we had vectors going around with no divergence, right? So that is pretty useful measure of the curl in the two-dimensional setup, especially when we do some other things later. Okay. So this is called the 2D curl. Just box it, keep it somewhere. We'll be soon coming back to it, maybe tomorrow. That's because the R and the Z components are 0. So if you go back to a 3D curve, those two terms just shut off. Okay. All right. So assuming that these ideas are clear, okay, let's just start some simple calculations with vector fields. Get slowly used to this rather strange concept. And what if you taken physics 1 and 2, or what is the usual expectation? I don't expect you, but you've taken physics 1 and 2, you probably would have seen it there with different names. Okay. But don't worry if you haven't. Section 4.2. Line integrals and work done. And this is something that was created from an electrical engineering point of view. So it has those flavors here and there. Okay. So suppose you have some kind of a path like this. Okay, so this is a curve C in R2 or R3. Okay. Between 2 points P and Q. So it could be a straight line, it could be a parabola, it could be a semicircle, it could even be closed, but right now let's just leave it open. Okay. And let's assume that we are going from P to Q. Okay, so it's fixing an orientation so that we don't have to keep fighting about it. So it's an oriented curve. So from P to Q. And suppose there is some kind of a vector field acting here. Okay, so F is a vector field. Let's just start with R2 to start with an easy case. Okay. So F equal to PQ in R2 be any vector field. And let's C be an oriented curve in R2. The word oriented just means that we are fixing the direction from P to Q. Okay. Oriented curve from P to Q. Now, there are two ways of doing what we are trying to do here. Okay. One, we can represent the C by its parametric form. So that R of t equal to x of t, y of t be the parametric form for this curve. T is a parameter. Yes, so for example, if you have a parabola y equal to x square, you could write t square. The picture. Let's take a small slice of this of length dr. So you can kind of see what I'm trying to do here. Slice up that entire path into small segments and take a very small segment of length dr. Okay. So F is a vector field. This is the distance. Then the work done by this vector field through the distance by physics would be just the dot product of those two. That's why I asked you if you have seen some physics, just to understand that work is force times displacement. Okay. So the work done So in reality, we're talking about an electrical field and carrying a charged particle from point P to point Q. Okay, but we don't want to think just in terms of electrostatics. That's why I'm talking about it as a generic case. Work done by this force F to move a particle through a distance dr. Okay. Remember, that's a vector because r is a vector, so any change in that has its own components x and y in terms of t. Okay. So through a distance dr is given by w change in work dw equal to f dot dr. This is a dot product of the vectors. Just because the dot product of force with displacement gives you the work done. Now, r is a vector that depends on t. So if you take t as the time that the particle is taking to travel from point P to point Q, okay, then dr by chain rule would be dr dt times dt. Okay, just can think about it as dividing and multiplying by dt, though it's a chain rule that is happening here because r is a function of t. Okay. And that's equal to r prime of t dt. So look at this term. This is the velocity. Okay. This is the time. Velocity times time is displacement. And force dot displacement is work. Okay. So this is f dot r prime of t dt. So the total work done in moving from point P to point Q from one end to the other is just the integral along that curve. Okay. It's some arbitrary curve. That's why it's called a line integral. Okay. So total work done is going to be the sum of the work done along all the small chunks along the oriented curve. Okay. And that will be the integral of f dot dr from point P to point Q. Which, using the chain rule we wrote there, can be written as the limits from t equal to whatever at this end of the curve. Okay, so let this correspond to t equal to a, and let this correspond to t equal to b. So the good thing is we have now converted the integral into a single integral in terms of t. T equal to a to t equal to b, f of r of t dot r prime of t dt. It looks very complicated when you look at it. There's like a lot of things. There's a vector field, there is this curve that is going into it, there's a derivative dotting it. All this means is you're taking the vector field and you are kind of replacing the x, y, and z components. Okay. So use x, y to rewrite f in terms of t. Okay. I don't want you to be kind of scared by saying this notation. Because at the end of the day, you want the integrand to be in terms of t uniformly. So r prime of t already is in terms of t. F was given in terms of x and y somehow, right? You are just trying to use this representation to write f in terms of t so that you have just a uniform function to integrate.
How do you take r prime of t if r of t is a multivariate?
Yeah, just take the derivatives of each term. Just calculus 1 now. Yeah. So the good thing is this is now just an integral in terms of t. Okay. So this is what you call as the line integral of f along the oriented curve C. And it computes the work done by f in taking a particle from point P to point Q. And to answer his question, and let me just write down what he asked. Okay, so if you're given R equal to X of t, Y of t, how do you find R prime? Well, just take the individual derivatives X prime of t and Y prime of t. If there's a Z, you would do Z prime of t. Okay, so that's probably what you did even in that parametric representation of surfaces. You took partial derivatives of each component. So that's what we will focus on tomorrow. Okay, we'll start doing the examples in that same worksheet. These are pretty routine calculations once you understand this concept here, to write everything in terms of this t. Okay, it's a pretty easy thing to do, though it looks scary when you look at it. Okay, so don't worry, don't be turned off by the appearance, and we will do the examples in worksheet 12 tomorrow. Okay, that's it for today. Try to not miss lectures, okay, because it's kind of a difficult concept and difficult section to get through. Don't fall behind at this point. You have done pretty well so far, so just hang on. Okay, thank you.